In this section, we have the opportunity to generalize the integral of an exponential function. The integral of a to the x dx, where a is a real number that is greater than 0 and not equal to 1, is given by a to the x divided by natural log of a plus c. Notice what happens when we apply this formula to the base e. We end up with e to the x divided by natural log of e plus c. Well, we know that the natural log of e is 1, so e to the x divided by 1 is e to the x plus c. So the integral formula that we have learned for integrating e to the x is actually a special case of this new basic rule. And as always, the chain rule will apply, or the substitution rule. I've got the wrong formula here in your notes, sorry about that. Let's fix this to the integral of a to the u du. We're going to end up with a to the u divided by natural log of the base a plus constant c. Now, the thing to remember about this formula is that u represents a function of x, and du represents also a function of x, the derivative of u. So let's apply this new formula to the example 4. Determine the following definite and indefinite integrals. We've got the integral from -1 to 1 of 10 to the x dx. Now, according to the formula, we're going to make a copy of the exponential exactly as it appears, and we're going to divide by the constant natural log of the base. Now, because this is a definite integral, we do not need the plus c, but we do need to evaluate upper limit minus lower limit. So one thing that we can do to simplify this is to factor out that constant 1 over natural log of 10, and then just evaluate 10 to the x from -1 to 1. Applying our fundamental theorem of calculus, we end up with upper limit 1 minus lower limit 10 to the -1. When we simplify, we have 1 over natural log of 10 times 10 minus 1/10. If we get a common denominator of 10, this is going to give us 100 minus 1 over 10, or 99 over 10. Probably the best way to write this in the most readable fashion would be 99 over 10 natural log of 10. On the next example, we can practice the substitution rule. Notice we do have an exponential function because we have a constant base raised to a variable exponent. But the exponent in this case, sine of x, is a function of x and not just x. So one thing that we can do is make a u substitution for that exponent. Now, if we do that, of course, we have to recognize the derivative of sine is cosine with respect to x. Now, our next goal is to rewrite this integral completely in terms of u. So before I do that, let's recognize that the secant in the denominator is really a cosine function inverted. So we could rewrite this as 4 to the sine of x times 1 over secant of x dx. If it helps that to write it like that, to recognize what I'm about to do, then we end up with 4 to the sine of x times cosine of x dx. That first step there you can skip if you can see how we get to that last step. So right here we end up with 4 to the u, and notice cosine of x dx is going to be replaced with du. Now observe, since we are moving from the variable x to the variable u, we will also need to update our limits of integration. So in the original integral, the variable of integration is x. So we can say when x is 0, u, here's the relationship between u and x, u is sine of 0. And of course, sine of 0 is 0. So my new lower limit of integration is 0. When x is pi over 2, then u is equal to sine of pi over 2. And of course, that's 1. So my new upper limit is 1. So when we integrate, we're going to make a copy of the exponential exactly as it appears. we're going to divide by natural log of the base, and again, it's not necessary to write plus c with a definite integral. Then we will evaluate from 0 to 1. So if you prefer, you can factor out the 1 over natural log of 4, and then simply evaluate 4 to the u from 0 to 1. So plugging in our upper limit of integration, we have 4 to the first. Now plugging in our lower limit of integration, we have 4 to the 0th power. From here on out, the rest is just arithmetic. Notice 4 to the 0th power is 1, and 4 minus 1 is 3. So we end up with 3 divided by natural log of 4. And of course, that is the exact value. We don't want to approximate unless an approximation is requested for the application or the specific problem. So that's the exact value of our definite integral. We will apply a similar technique for example C. Notice we do have an exponential function that is a constant base 5, and in the exponent position we have a function of x. So we'll make the substitution. Let u represent the exponent. I'm going to take the entire function that's there. Then the derivative with respect to u, applying our power rule, would be 2 times the base x plus 2, decrease the exponent by 1. Chain rule says multiply by the derivative of the base, which is just 1 dx. Or if I simplify that, I'm going to go ahead and distribute the 2. We have, or let's not distribute the 2, 2 times x plus 2 dx. So after replacing this part with its equivalent in terms of u, notice the leftovers here are x plus 2 times dx, and I've got that right here. So I'm going to go ahead and isolate that by dividing both sides by 2. We have 1/2 du equals x plus 2 dx. So at this point, we're ready to rewrite this indefinite integral in terms of u. And remember, I always change colors when I'm going from one variable to the next, so I really want to catch your attention that that's a major change in our process here. So I'm going to start with the expression 5 to the x plus 2 squared. We can rewrite that as 5 to the u. Now the leftovers, x plus 2 dx, we discovered is equivalent to 1/2 du. So we have 5 to the u times 1/2 du. Since 1/2 is simply a constant coefficient, we can move that there in front of the integral sign, and we're down to our basic integration formula. This is our new formula. To integrate 5 to the u, we're going to make a copy of that exponential, and we're going to divide by natural log of the base because it's something other than e. Then, because this is an indefinite integral, we are going to add our constant of integration. And because this one is not a definite integral, we do need to go back and recover our original variable. So I need to replace u with its equivalent in terms of x, since the original variable of our formula was x. So we can rewrite this as 1/2 times 5 to the x plus 2 squared divided by natural log of 5 plus c. And I suppose the most readable way to write this would be 5 to the x plus 2 squared divided by 2 natural log of 5 plus c. And that's the value of our indefinite integral. Now remember, it's always a good practice to check your indefinite integrals with differentiation. So I'm going to go back. I'm going to take my result and differentiate it with respect to x. Remember, this accomplishes two things. Number one, I can check my answer. Number two, I can practice my differentiation skills. So first of all, I'm going to look at that 1 over 2 natural log of 5 as simply a constant and filter through that to the derivative. Then we need to differentiate this exponential function with a base other than e. Now, to differentiate our exponential function, we make a copy of the exponential function exactly as it appears. We multiply by natural log of the base, and then we multiply by the derivative of the exponent. So the derivative of the exponent, I'm going to try and sneak it in over here, running out of room, is 2 times x plus 2. Sorry about that. I hope you can read it. Now, the 2 that I have right here is a factor. I'm going to cancel it with the 2 that I have here. The natural log of 5, another factor, it's going to cancel with this one here. So to clean it up, we end up with 5 to the x plus 2 squared times x plus 2. And notice that matches the original integrand. It's in a different order, but we know multiplication is commutative. So our indefinite integral result is correct. So let's finish up this particular section with an application. Example 5. A lake has a population of 500 fish at time t equals 0. So we could say the initial population is 500 fish. The fish population grows at a rate of dp over dt equals 0.1p. Notice I don't have the population function, but I have the rate of change of the population function. That means we're dealing with a differential equation here. Predict how long it will take for the population to reach 1,000 fish. Well, to answer that question, we need to find p of t, our population function. So we're going to solve this differential equation. dp over dt equals 0.1p. Now, one important thing to point out here that we can obtain from this Leibniz notation is that the independent variable is t and the dependent variable is p. So I cannot integrate both sides directly with respect to t, the independent variable, because on the right side I have the dependent variable. So this particular differential equation calls for the solution method of separation of variables. That means I need all of the p's over there on the left and all of the t's over there on the right. So this is going to look like 1 over p dp equals 0.1 dt. So I have divided both sides by the variable p, and I have multiplied both sides by the differential factor dt. Now, as far as the 0.1 goes, you can take it to the left, you can leave it on the right. It doesn't really matter because it's a constant. But at this point, we can now integrate both sides with respect to the individual variables. On the left side, we have the integral of 1 over p dp. We know that's the natural log of the absolute value of p. And I'm not going to write the plus c at this point, even though it is an indefinite integral, because we'll accomplish that over here on this side. On this side, when we integrate with respect to the variable t, we have 0.1t. Now we can include our constant of integration. If I had added a c to the left side as well, eventually I'd combine those constants on one side. So adding c to the right side is sufficient to cover all of your necessary arbitrary constants. Now remember, our goal is to find our population function. So I need to solve for p. We can go ahead and convert this into exponential form. So p is equal to e to the 0.1t plus c. Again, we just went from logarithmic form to exponential form. Now, once I do that, the absolute values around the p are no longer necessary because e raised to a power is always a positive number. And as we have seen before, we can manipulate that constant c in the exponent by separating it into the product of two exponential functions. Remember, if we see like bases, we would add the exponents and combine it like so. So at this point, I'm just applying that basic rule in reverse. Now, once we have it in this fashion, we can recognize that e to the c, a constant to a constant, is a new constant. So I'm simply going to replace that with c, a new constant, and keep the e to the 0.1t the same. So we have our population function. We have p equals c to the 0.1t, but I do want to point out that is a function of t. The population p depends on time t. So I'm going to refine it and write it in function notation. Now, before I can answer the question about how long it's going to take for the population to reach 1,000 fish, I need to find that arbitrary constant c. And we'll be able to do that by applying our initial condition. So our initial condition, IC, at time 0, the population is 500 fish. So we're going to plug 500 in for the population, and we're going to plug 0 in for t. So we have e raised to the 0th power, which of course is equal to 1, So we have c times 1 equals 500, or c equals 500. So if we go back and refine our, remember this is called a general solution, we're going to refine that to a particular solution by plugging in the value we found for c. Again, that is our particular solution. So just based on knowing how fast this population is changing and the initial population, we can now predict the population of that lake according to this model at any point in the future. Our question is how long, that is, what is t when the population is 1,000 fish? So we need to find p of what t equals 1,000. So I'm going to set my population equal to 1,000, and I'm going to solve for t. The first thing we can do here is divide both sides by 500. So we have 2 equals e to the 0.1 t. We can then convert to logarithmic form. Natural log of 2 equals 0.1 t. So again, we're just going from exponential form to logarithmic form. To finish, we need to divide both sides by 0.1. So our t value here is natural log of 2 divided by 0.1. Now, in the statement of this particular problem, we have not been told the units for t. So let's just assume that it is days. So I'm going to assume t is time in days. So it's going to take natural log of 2 divided by 0.1 days for the fish population to reach 1,000. However, we need to go ahead and approximate that just so our brains understand how much time is that. This would be 6.9 approximately days. And I just rounded there at random to the nearest tenth. So you can see here that we solved a differential equation using the separation of variables method, and we got to examine an interesting exponential function.